Okay, thanks again, everyone, for bearing with me. I'm Tom Cooper. I'm Vice President of Strategic Partnerships for NoTraffic, and NoTraffic is the world's first fully autonomous traffic management service platform. We have a webinar series that looks at harnessing the power of AI to resolve tough traffic challenges. And today's topic is going to be Chapter 2, Harnessing AI to Resolve Traffic Detection Challenges. I'll just give a very brief recap of Chapter 1 because it has direct bearing on what we're talking about here today. In our journey of becoming the first fully autonomous traffic management service platform, we needed a very good detection form to feed our algorithms to optimize traffic, and we simply found it wasn't available. So our journey wasn't to become a hardware company, but part of what we had to do was develop sensors that can give us the kind of robust data we need to optimize traffic very efficiently. So Chapter 1 was called Unprecedented Change, New Opportunities for AI Traffic Optimization. And we looked at different examples of using AI to solve some very, very challenging traffic situations. Just a point of information, that video is on the YouTube channel. I literally have tens of viewers right now, so I'm looking forward to some more so I can get my royalties from YouTube. But I think you'll find that pretty interesting. So take a look at that when you have an opportunity. So what we talked about in the first session was complex challenges, things like crossing arterials with a lot of side street demand and grids with pushing and pulling priorities, things like TSP and pedestrian movements, and then getting these very complex environments with a lot of interdependencies with multimodality and highways and EV preemptions and EVP and rail crossings, et cetera. Things that are very, very complex to handle with the traditional methodologies of creating timing plans and doing studies to drive the timing plans and trying to keep them up to date. Those models sort of worked in the world where there's a lot less variability, and today traffic is so unpredictable, and that's really a major challenge and concern for a lot of planners. So the whole idea is doing this without new timing plans. I talked about our journey and getting to this fully autonomous environment. We had to start building hardware to do things that simply weren't available in the marketplace. So it starts out with this sensor, which kind of started our process of thinking about challenges for detection that were validated by a lot of the agencies that we deal with. So using AI-based sensors, heavy-duty processing on the edge to process things about approaching robo-users, classifying them by pedestrians, vehicles, and cyclists, and capturing trajectories, giving us a full view of the intersection, and taking that data and pushing into an optimization engine that uses deep learning AI, basically simulates what's happening by the human mind, and looking at all the permutations of possibilities for moving traffic based upon the local data and the global data with platoon movements, and then fundamentally driven by policies that are set by the agency. So in a nutshell, this whole platform is driven by policies and not timing plans. And those policies obviously come from the agencies and are defined to meet the agency's objectives, which always should be starting with safety, right? And part of it too is we don't violate any of the safety constraints. So fundamentally in this journey, this was a major problem for us, finding detection that was accurate and can get us the robust data we needed to drive these algorithms. And this continuously is validated by the agencies that we talk with, that detection continues to be one of their most significant challenges in managing traffic effectively and also safely. So if we take a look at some statistics, it's funny that you'll see vendors talk about our accuracy 3%, 4%, 5%. Well, the question is when. So even if you're inaccurate for 2% of the time, that's still a week out of the year. So if that week happens to be during the early spring and late fall when you have low azimuth lighting and you get continuous false calls, that's one thing. But that inaccuracy is during times where, let's say it's night and vehicles aren't detected and motorists just are frustrated and start running red lights. That becomes a major issue. So this was all the factor in us figuring that we needed to develop a platform that effectively could deal with all the situations that we may possibly find related to detection technology. So in this example, if I have 2% inaccuracy with a 45,000 AD2 car, I'm missing 38 cars per hour. And if that's, again, it's at nighttime or times where there's inclement weather, that could be a major issue in terms of performance and also safety, of course. So look at the different detection types, and we'll talk about specific things that we keep hearing from agencies that are particularly challenging about these detection types. But we'll talk first of all about the venerable inductive loop. A wire in the ground. Great and wonderful when they work. That's high detection accuracy when they're calibrated, but very high maintenance costs. So many agencies we talk to simply have failed system loops, or it's just it can't keep up with the cost of maintaining them. So, the world is starting to migrate away from that in many areas, specifically because of the maintenance costs. And in its day, it can count presence, but it can't count queues. I certainly can't do advanced functions like capturing trajectories or classifying vehicles. Another major problem today is it can't detect low ferrous content objects, bicycles, micromobility, scooters, pedestrians, and what have you. So major challenge. It did served us well when volumes were low and expectations were just as low as well. Then enter video detection. So obviously video detection as a improvement upon loops, basically simulating loops at the stop bar. It can do some classifications and counts. Tracking is beginning to emerge, but it's really reliant on the typical legacy systems, reliant on a lot of back-end processing to do all the advanced classifications I'm going to talk about with edge-based sensors. Major issues are it's affected by climatic conditions, night, shadowing, sun glare, fog, heavy rain, camera movements. And there are also things like lenses need to be cleaned. So there are physical considerations to dealing with video detection. And there's ongoing maintenance, and really needs a knowledge of the system to really keep video detection systems running accurately. So other things have entered our world. Radar. So radar can accurately track roadway object speeds and classifications in some circumstances. It detects in poor visible conditions, but there are also some challenges with that in terms of monitoring and some areas where the physics behind radar simply don't work because of things like multipathing and spilling over between vehicles. So it's a point level solution for a very specific type of problem. And there are other solutions that use infrared, so thermal imaging, for example, relatively simple to deploy, can detect vehicles in poor visual conditions, but it also has some challenges. As a matter of fact, I was talking to an agency in California last week about a specific instance where they tried thermal at an intersection, and it doesn't work when the ground is relatively cold, and cold vehicles pull up to that. So that's an issue. There's no disparity between temperatures. And in Texas, for example, you've got puddles of heat that just simply can't discern vehicles. And there are also issues with blindness caused by a certain amount of light fog. So these singular detection methodologies typically have compromises. And in the year 2020, agencies are still evaluating detection technologies to solve problems they haven't been able to solve. And that's the same journey that we were on when we decided to develop the sensor platform that's based upon AI-based computing at the edge. So in our world, we look at multiple input technologies. So by using radar and video, we can detect trajectories, and we have a very high sample rate. And we look at all the objects in the intersection and determine their position, their classifications, and lets us do a lot of things using AI harness to those input methodologies to give very high accuracy in terms of position and occupancy. But it also gives the ability to have the system self-calibrate. One of the major challenges with these more advanced technologies, and more advanced being more advanced than loops, is it requires intimate knowledge of the system and the setup and the ongoing maintenance to keep them going. So in the typical world of legacy detection, the single inputs detection methodologies have issues. So example, a current state-of-the-art quote unquote detection system that requires physical geolocated zones to be set up to count vehicles and classify them. And if the camera moves, if it's occluded, whatever, then this starts falling apart pretty quickly. And unless you're observing that on a regular basis, you may now have no idea that there are particularly issues happening at this intersection, if there are problems, unless motorists complain. The other methodologies of using these geo-referenced polygons, of having to create them and put them in place. So this, just a simple setup, very complex with most of these advanced detection technologies, then the ongoing maintenance requires you to have a fairly high level of knowledge about how these systems are set up and managed. And we maintain there's a better way to do this. So by using AI fused with multiple input technologies, it offers auto setup capability and continuous self-calibration. So I do not have to go back. I don't have to worry about maintenance unless the very worst case scenario, let's say maybe a hurricane comes by or a truck knocks something down, what have you. By using a very high sample rate and deep learning analytics on the edge, I have more time to think about how I'm classifying users, what the needs are at the intersection to serve green time, to detect and to count and effectively move traffic. And this idea of trajectory tracking. If I can capture trajectories, I could do things like let the system learn about how vehicles approach and what phases they're assigned to. But I'm also able to make determinations about anomalous behaviors at the intersection. So what I'm submitting is that this should just be more than detection. It should be an alerting mechanism to let you know that anomalous things have happened. We're going to get back to that topic here in a couple of minutes. Classifying user types, very important, because obviously there might be different phase assignments or different treatments or policies set by the types of users that are being sensed and detected at the intersections. And there's a function called a virtual smart loop that we put in place that in its worst possible scenario, if we know a little about what's happening, the climatic conditions are horrendous, but we can still determine with a very high degree of accuracy, is there actually somebody at the intersection so we can serve them green time. So how this works, and I'll give you, this is a kind of a depiction of what our mind's eye, our systems, our sensors see. So on the left-hand side of the screen, you're going to see a view of what's actually happening from the video intake side. So the video intake side, you're going to see is going to start classifying the objects. On the right-hand side, this is actually a view of the radar world where it's actually capturing trajectories. Now, the output of this is something called a BSM, or a virtual basic safety message, which is the underpinnings of connected autonomous vehicle technology. But fundamentally, what's happening here is this fusion between video and radar, capturing trajectories and classifying vehicles. So you'll see here, as we're going along, the objects are coming into view, they're being classified, trajectories are being captured. So in this moment, I continue to do the detection and sensing at the intersection. Here I'm capturing pedestrians, but I have ideas about how the objects are moving, their trajectories, and I can let the AI start learning about how I do things like zone placements and manage zone placements and not have to worry about continually maintaining those. So an example of fusing those pieces together gives you a high degree of accuracy and a lot of information about what happens at the intersection. The other aspect of this too is it gives you a safety insight. So it shouldn't be a single purpose system, and we maintain that since you have really smart sensing at the intersections, you should be able to capture anomalous behavior. So here's an example of standard detection. We're looking for an approach, but we noticed something anomalous, a wrong way runner. So very fortunately, there wasn't any incident here, but that was something that's detected, alerted, and alerts are sent out immediately to the operator, the system traffic engineers. They should obviously do something to address this. And if you notice, there's a bag signal ahead, so I would have put up some temporary signage about what's happening at the intersection. Another example, so middle of the night, maybe this is a safety issue to be addressed, and I will caution you, there is an incident here. It's only property damage, and you'll see another example of, since I'm capturing trajectories, and I know where vehicles typically are functioning, things like this, that's anomalous behavior that automatically generate an alert that could do a couple of things. It give you more time to respond, the first responders, but also gives you safety insights to what's happening at the intersection level. So we have some traditional challenges, nature-made and human-made. So the climatic conditions, some of them are obvious, some of them are not. For example, mist, fog. That's a major challenge for most modes of video detection. And even some things like thermal we talked about earlier, major challenges and dealing with that. So how do I actually count into this? If I have a long queue sitting behind here, I actually do have vehicles in the back you can't possibly see. That's a challenge that still hasn't been surmounted by the legacy types of detections that are in the marketplace right now. Things like this, mist on the lens, condensation on the lens. Now with AI, what I can do is I can continuously learn about what's happening here, and I can sense through that and still do classifications where other hard-coded sorts of algorithms simply can't deal with this kind of a situation. The only recourse might be to go out and dry off a lens. Here's an example. The bane of video detection is shadowing. So we talked about that example of low azimuth lighting in the early spring and the late fall, causing false positives. Major issue that unless I've got multiple methodologies, I might not be able to effectively classify and count and detect vehicles based upon this, or I may just have a slew of false calls, which obviously causes inefficiencies in the transportation network. Another example of things caused by nature, this nighttime with wet sidewalks and bright lights, and this is a perennial challenge with video, is discerning things like this. Is this just a splash or a shadow, or is that actually a vehicle? And if that's a vehicle and I skipped it, that's got a whole cascading effect of safety and optimization. And here's an example from a current quote unquote state-of-the-art traditional video detection system, which has major issues detecting vehicles at night. So I'll show this to you, and there'll be a illegal red light running here. It's not going to cause an incident. I'll let you know about that. But this is an example of what poor detection can actually cause in your network. So this is time collapse. This is going to be a 7-minute period. Driver's waiting and waiting and waiting and waiting and waiting, and 7 minutes later, decides to run the red light. So obviously that's not a good thing. That's a safety concern, but it's the current state of technology by using these single input methodologies causes that sort of an outcome. And we've got human-made conditions. So a classic issue and something we can keep hearing about time and time again is work zones. Where are work zones set up in my agency? Where are they on the streets? Very impactful to traffic. So typically you don't hear about them, or you hear about them from motorist complaints, but AI has the capability, AI fused with these different modalities of sensing, has the capability to know, number one, this is an anomalous situation. Maybe I should alert about that. And you can also apply logic behind that. It says, in this case, then maybe I stop detecting and coming up with a phase call for this specific lane. So something that you'd have to deal with manually in an agency, or not respond to it, and just let motors deal with the after effects. Another example of spillback. So typically in detection, you might be just doing detection for this turn queue, but you're seeing behind that is that's something that's not typically coded for in this environment. So having a system that could automatically learn about this, I maintain a system should never let you get to this point, serving green time equitably, but another example of some human-made challenges. Then things like this, where you've got, again, this shadowing issue. Perennial challenge for video detection are these shadows, which can cause false positives. In this case, it's not a hard edge line. So if you're coding for things like hard edge lines, assuming that's a vehicle, that's particularly challenging without algorithms to figure that out if it's pixel-based. And again, another area where you could potentially have false positives and not have the most effective operation at the intersections. And then things like this, so objects like bicycles hitting the roadways, is this one classifying them and being able to apply a priority to them. So in our world, we might have a bicyclist priority, where if I've got a certain threshold of bicyclists waiting, bicyclists are sometimes known to not obey traffic signals, so you might want to give them a priority to move through. Things like this, where you've got shutdowns, not work zone related, but things like this we're seeing more and more happen at our intersections. So having an alert about this would be nice to know, so that it obviously could have impact on traffic. And if you have a system that can deal with this, potentially you could have some rerouting based upon conditions where it's not the most optimal for traffic flow. And things like this. I mean, I think people actually do ride these. So again, another example of classifying this as a specific user type, of vulnerable robot user, giving them priority so they can traverse the intersection safely. So fusing machine vision with edge-based AI analytics, we're creating something called a sensor. So that's the nomenclature we like to use. It's taking multiple inputs and using deep learning and high accuracy in all conditions. So by using radar, and specifically we pick these two forms of physics because they've got specific trade-offs, radar and video, but those trade-offs are handled extremely well by the compilation of the two of them with analytics sitting on top of us. From a physics perspective, all the objects and all the climatic conditions that need to be handled are handled extremely well, and using advanced AI algorithms to deal with that to come up with very high accuracy. So that, of course, is always better than these singular detection methodologies, video detection or radar or thermal or loops. Where we are today is now general use components are available that make this technology cost effective. So at the sensors, it's high-end AI-based silicon that can process on the edge without having to have a large pipe for back-end server access. It all happens at the edge. All that silicon has come down significantly in prices. So now these types of advanced technologies are at the same price point or lower than these legacy sorts of solutions. And by having a managed service offering, which we are, as edge cases, things that the AI hasn't learned yet, since we've got monitoring about alerts and anomalous situations, they can be trained into the system. So you continue to get this updating and this learning of edge cases that may not have been contemplated anywhere else. So it gives you these high availability levels, 4 nines and 5 nines. So let me come back again to statistics. So we talked about just this theoretical statistics of accuracy detection, but it gets real when you start thinking about what's the impact on safety. 2019, we lost 36,120 lives in our roadways. 40% of those happen at intersections, 20% of fatalities happen at intersections. That's 7,224 lives. Pedestrian fatalities are going up, specific intersections. Very, very bad thing. If you look at crash deaths from running red lights, 2,023 lives were lost last year from red light running. I am not submitting that this AI technology is going to eliminate these, but if it reduces 200, 100, 50, or 1, I think it's worth it, and I think we need to do better with our detection technologies. That, coupled with the operational efficiencies, makes it something I think we need to consider for our detection methodologies moving forward. So again, we take a look at this video, it takes on a whole new meaning when we think about safety at the intersections. So 7 minutes later, if you had been in a crosswalk at night wearing dark clothing, that could have been a seriously horrendous incident. So in summary, single sensing legacy technology, it can perform poorly in some conditions that we had talked about, and it significantly impacts safety and traffic flow. By using multiple sensory inputs and deep learning AI, it lets you process all the data at the intersection level to look at all the operations and give you very high accuracy in all conditions, and then do these advanced features like the optimization using that data and the alerts using that data, gauging safety insights. And then it's a managed service platform. So there are humans in edge cases that can't be analyzed by the current state of the art AI. There are always humans in this chain of looking at that. So that's a very valuable piece of this. It's a continuously monitored system 24/7/365, which gives unparalleled safety and accuracy with detection forms. So with that, I thank you. If you have any questions, I'll go to the chat window here and see what we've got. Can your AI-assisted image enhancement prior to interfacing for object classification? Yes, so we do object classification. That's actually part of this, if I think I understood the question correctly. So that's a big piece of this, and I can, if you're curious, send me an email to tom@notraffic.tech. I can show you the type of classifications that we developed in the system and give you some more depth on how the system typically interlays together. Another question is this AI component. So this sensor is actually part of our optimization platform, and it is a service, and it could be used as a sensor itself, but it's also used in combination with multiple other feature sets of the platform, which include obviously the optimization, communications, which are built into the platform, and other advanced features like emergency vehicle preemption support and transit signal priority support. So the next question was, is this system best deployed at an isolated intersection, corridor, or grid? Yes, that's the answer. So there's definite benefit for delay reduction and detection accuracy at a single intersection. As you start moving to arterials, then you get the benefits of the coordinated movements being very well interlaced with the side street movements. So you bring out overall delay. One of the major challenges that was dealing with grids. So this architecture can also scale up to deal with grids. The fundamental difference between this and other methodologies is I do not have to build timing plans, and it scales very smoothly by just adding additional intersections. So great question. This solves all those use cases. All right, well, I think that's the end of questions. Everyone, thank you very much for your time. I certainly appreciate that. Again, if you have any questions, please email me at tom@notraffic.tech. We'll have some future webinars talking about safety insights from AI. We'll go a lot more depth in that. And we're also going to look at the connected autonomous vehicle support from our platform. Again, thank you very much. Please visit our YouTube channel for the previous episode, and have a great day.